It is our great pleasure to have the first seminar for this semester, and we have a special guest came from Hong Kong, the City University of Hong Kong, and she is Miss Kelly Zhang from Hong Kong. Actually, Miss Zhang is a student of. Okay. อ๋อผมนึกว่าตรงนี้ Okay, we will wait for another 3 minutes, okay, for our attendance, all right? And we also have a group of our guests from Hong Kong and China, right? Can you say hi, Professor Benny? I think we can hear you as well. Okay, Professor Benny. And actually, Dr. Vanida is here to meet you as well. จันเข้าไปทางนั้นได้ครับต้องไปหน้าคอมก็จะเห็นหน้าอาจารย์แล้วก็ไปที่หน้าคอมต้องเข้าไปที่หน้าคอมของเขาตรงนี้อาจารย์ไหนเนี่ยฮะหน้าคอมDr. Vanida will say hi to you, Benny.
Hello, can you hear me? Benny.
เนี่ยฮะเขาบอกแล้วครับว่าเขาได้ยินเขาพูดกลับมาจะได้ยินไหมครับ
I didn't hear you.
But at least you see her, okay?
You recognize me? Do you recognize me?
Of course.
And I will give you something that Kelly would bring to you, okay? But she said that you would get that next year. Sorry. Oh, right. I'm waiting for you, okay? So be sure to be here, okay? Now, Ratinan is the department head, so he can help you with everything.
ท่านอื่นๆที่เข้ามาร่วมฟังนะครับเชิญรับขนมของว่างก่อนได้เลยนะครับแล้วก็จะได้มาลงทะเบียนตรงนี้ด้วยเนาะระหว่างที่เดี๋ยวเรารออีกสัก1 นาทีนะครับ so wait for another 1 minute รบกวนช่วยลงทะเบียนด้วยนะครับแล้วก็รับของว่างด้านหน้าห้องนี้ได้เลยนะครับห้องนี้รับประทานขนมได้นะครับทานน้ำได้เลยได้เชิญเลยนะครับLet us wait for another 1 minute, okay, for the audience as well.ใครที่ลงทะเบียนแล้วก็เรียบร้อยนะครับแต่ว่าใครมารับของว่างก็เชิญได้เลยนะครับOkay, guys, as I told you that it is our great pleasure to welcome Miss Kelly Zhang from the City University of Hong Kong. Actually, Miss Zhang is a student, a PhD student of Professor Benny Hong, who used to came here to give a talk about the finite integration method for a few years ago. So right now, her talk today will also extension of the finite integration method, but this one it will be the general finite integration method for high-dimensional option pricing. So please enjoy her talk.
Okay, so thanks a lot for Professor Ratina's introduction. And my name is Zhang Kexin, and you can feel free to call me Kelly. I'm currently the PhD student from the Department of Mathematics from the City University of Hong Kong, and I will expect to graduate next year. So today, the topic I would like to share with everyone is the general finite integration method for high-dimensional option pricing, which is a recent research output by our research team. So today's, sorry, this may not work. Okay, fine. So in today's talk, I will separate it into 4 parts you can see from the top. The first part is a brief introduction on the option pricing by the Black-Scholes model, which is our application here. And then the second part is so-called the Finite Integration Method, and FIM in short. Then the GFIM, Generalized Finite Integration Method, is a method we recently developed based on the FIM. And then the final part should be the numerical experience. So we start with section 1. The Black-Scholes equation proposed by Black and Scholes in 1973 is a worldwide well-known the PDE model for evaluating the fair price or the non-arbitrage price of the simple vanilla option. Here in this box you can see is the Black-Scholes model for n underlying assets. This n can be any positive integer, which means that let S be the price of the underlying asset I, and V here we contains n stocks together with a time variable altogether to be represent the option price, and sigma is the volatility of the asset, rho is a correlation between asset I and J, and R be the risk-free interest rate. Then the Black-Scholes equation for the n underlying assets will be this long partial differential equation. So in this study, I'd like to share with everyone, we mainly focus on the single asset which we only contains one stock, S1, and also the 2 assets option, S2, S1 and S2. So for the single asset, it is very similar. It is similar as the previous one, but simplified one. And the V stands for the option price, S1 from 0 up to positive infinity, because the stock price can increase. In the theory, it should be increased up to the positive infinity. And here, this capital T is the time to maturity, which means that we have to exercise the option at this time. So for the European put option, which means that the investor have to, and they can only exercise the option at the maturity time, capital T. So the value of the option will be the maximum between the strike price E1 minus S1 together with 0. This is a terminal point boundary. And for the boundary conditions in between, for S1 and any T in between the 0 and capital T, it should be this piecewise function, right? When S1 goes to infinity, the value of the option will be 0. But when S1 is small, it should be like the strike price times the discounted rate. Okay, so the former one is the European option, and this is the American. The American option means that the terminal payoff valuation and boundary conditions are the same as the European option, except with an extra early exercise condition at any time t, which means that you can hold this option, and for the European, you can only exercise it at capital T, but for American option, you can exercise it any time in between. So here, an optimal exercise stock value S1, we denote it as BT, boundary, means B stands for the boundary, exists for American option, where BT is an unknown free boundary to be determined. So this is the difference between the European and American one. Then for the 2 asset option, actually there are many kinds of them, and here in our study, we focus on what we call the exchange option, and I will illustrate it later in the numerical part. So for the 2 asset option, we can see this equation here with a correlation, value, and 2 stock price. Here I have to mention that is that in our numerical study, because we cannot determine this positive infinity, we have to truncate it into 0 up to L1 and 0 up to L2, which here this L1 and L2 will be sufficiently large in case to, so that they can perform as a positive infinity, but actually not. So the condition, for the terminal condition with capital T and the boundary conditions, because we have four boundary conditions with 2 different assets, we have f1 up to f5. These are our boundary formulas. And these f functions are highly related to which kind of option you are going to work with. So different option, different two asset option, different boundary equation you might choose. Okay, so that's the end for the first part, and then we can take a look at the finite integration method. Finite integration method, the first paper was published in 2013, and later I will show you the paper's topic, and in case you are interested, you can go further. So the formulation of finite integration method is that when we let ux to be the function, then x1 up to xn be the uniformly distributed nodal points. And here we let this h to be the difference between two neighbor nodal points. Okay? So in the traditional finite difference methods, FDM, we calculate the derivative of uxk. We approximate it by using this fractional function. But for the finite integration method, the key idea is that we change this kind of differential equation into an integration part. So which means that we integrate this u from x1 up to xk. Xk is any nodal points in between. And then we can expand it into summation of these k minus 1 integrals in equation 7. And then, for example, we can approximate this one by, for example, trapezoidal rule, and also we can use other kinds of approximation. Okay, then it is in equation 8. Then we can rewrite this kind of summation of integrals into a matrix form. That is, we expand this equation 9. We expand it, and we can see only the first term and the last term have the parameter h over 2 in front of it. And then all of in middle have the parameter h. So based on the equation 10, we can rewrite it into a matrix form. The matrix multiplication between the row matrix together with the column matrix. Okay? And then because we have overall n nodal points, but here we just pick k in between. So therefore, for the rest of the part, here we write it in blue. We added extra zeros at the end of the row vector, row matrix, and the uxk plus 1 up to uxn at the end of the vector matrix. So, okay. And then we can substitute each nodal point, that is x1 up to xn, into the integral of the integral of u from x1 up to x, which means that we replace this x by any nodal points here. Then we can have this whole part in equation 13. And the first matrix we get here, we denote it as A, which A is an n times n integration matrix. We define in the finite integration method. And then this u should be the function evaluated at each nodal point. So the key part here is that we construct this kind of A here. Okay, then because here we just show that if we integrate it once, but in the real example, if we want to integrate it in multiple times, then we can define the multiple integrals in equation 15, and then we can substitute each nodal point into the i's multiple integral. We can denote it as u to the power of I, x. Then we can form it the similar as before, but here this integration matrix has the power I. So it's the same idea, but if we integrate it more times, it will be a i's power. So to illustrate it better, here is a toy example. That is, here is an ODE, which is the second derivative of ux plus ux equals to 0 for x from 0 to 1 in between. And with conditions, the lower bound condition u0 equals to sine 0 and u1 equals to sine 1. Then how to apply the finite integration method. So the first step is that we integrate this ODE with respect to x for 2 times, because this is second order, right? So we integrate it for twice. Then the first term, second order differentiation integrated twice will be ux itself. Then the second part should be this double integral. Then on the right-hand side, because we integrated for twice, we have C0 and C1, which are our arbitrary constants. So therefore, substitute each nodal point into the integrated equation listed here in 20. We will have this kind of form, right? Because we integrated for twice, this A is our integration matrix we defined before. So here, then we can rewrite the equation in the matrix form. In the matrix form here, this Iij is the element of the matrix A0 plus A to the power of 2, right? And then we write this one column here, x1 up to xn here, and then this negative C0, negative C1 here, and the right-hand side is still the 0 vector. Because our ODE has a boundary condition, we have to add them up in our matrix. So here we can see this red part is that we add up the U0 equals to sine 0 here, and then U1 equals to sine 1 here, because we separated it into n nodal point. So the first one will be our left-hand side boundary, the last one will be our right-hand side boundary. So overall, for solving this n plus 2 times n plus 2 resultant matrix here, then we can determine our ux1 up to uxn and arbitrary terms c0 and c1. Okay. So here, these u functions are the approximate solutions of function ux evaluated at each nodal point. So overall, it finished what we did by the finite integration method. So the key part is that we change from the original differential equation into this resultant matrix formed by the integration. So this is the key part, how the FIM do. So also we would like to share about the convergence estimation of the FIM. So because here, let me go back. Here we can use the trapezoidal rule to estimate it, and also we can use others. Here, if we can use the same-chance formula to interpolate this function f, then we can get this equation 24. Then we can calculate the first order integration and second order integration here in equation 25 and 26. Then later we can also calculate the error terms by taking the derivative here. Although I may skip some steps here because it is kind of tedious in the equation 27. So for the FIM method with projector symptoms rule, it may have the convergence order of OH to the power of 4. And if you use more simpler projector trapezoidal rule, then the FIM has a convergence order of OH to the power of 2. And even further improved order of convergence can be achieved if we use like higher order projector rules such as Chebyshev polynomial. So it is very flexible actually. Okay, so after talk about the FIM, you may wonder what is generalized finite integration method is. So in this section, I would like to introduce how we generalize it. So the limitation for the FIM is that we use uniformly distributed nodal points, right? X1 up to xn. But here for the GFIM, we actually write this approximate, or we call the approximate solution, into a piecewise polynomial of degree p with n minus p, this overall n minus p polynomials, which means that for this approximate, we write it in the piecewise function. So where this uj is the subpolynomial of degree p defined on this subinterval. Okay, so this integration matrix can now be obtained by integrating the piecewise polynomial from x1, it is the same as the FIM, to each nodal point xk with respect to k. Okay. And then, for example, we consider a subpolynomial uj here in between. Then this is a polynomial we get. Here a is the unknown coefficient of the subpolynomial, and we write it into a p times 1 vector matrix. And here our X is a 1 times P row matrix. So we write this Uj equals to X times A. X is a row matrix, and A is a vector matrix. Then we can substitute P plus 1 nodal points, xj up to xj plus P into the subpolynomial Uj. Then we have this representation, Uj equals to xj, this is xj is represented here in the matrix, times this unknown coefficients A. Then we can further represent this A by the inverse of xj times uj. So here xj is a P plus 1 square matrix. And then we substitute this equation 32 into the subpolynomial uj. And we can get our estimation of this ujx into this Lagrange basis function. So this one is very important in our real practice because this kind of approximate help us to find any point within this whole time interval to get its approximate value, rather than the in the traditional FIM, only if this x is what you selected as a nodal point, you can get the value. But here with this representation, you can get any value in between. So this is what is important for the GFIM. Then we can denote U as this matrix. This matrix is just used in the calculation here. For the, I have to say that for the detailed proof for this whole part, we can find in the first paper of the GFIM. I will show you later. Okay, so denote U as this square matrix, and then integrate this subpolynomial uj from xj up to x and x. We can have this part, and here the second x and second xj are just vectors. The first x and xj are just values. Okay, then we can to simplify the representation, we can introduce an alpha here. Alpha will be like this piecewise function, and overall our representation for the integration of each sub interval will be represented in the equation 36. Okay, then consider any nodal point xk in between and rk be the residual value as of k minus 1 over p, and sk be the number of sub-intervals. Then we can integrate the piecewise polynomial u hat of degree p, defining equation 28 is this piecewise function. Okay, and then we integrate it all together, which means that we separate it into the integration of u1 and the integration of u1 plus rk plus I. Also, this proof can be found in the paper later I introduced. And because we write this formal part into alpha, so we can represent it by the alpha to omit this kind of integral notations. Okay, then we get this equation 39. And then for further simplification, we can let the alpha bar into this what we get within this bracket. We denote it as alpha 1 bar. And then because this just for the nodal points xk, then for all of these nodal points, we form them all together. We can get this part, the matrix of alpha bar times the matrix of u function, then equals to AU. A here is the n times n integration matrix defined in GFIM, this whole part. Okay, here A is a p row shift lower triangular matrix, which makes the inversion of the matrix easy to be achieved. This means that for the further calculation, we may want to calculate the inverse of this A. So here we say we can guarantee that A is easy to calculate the inverse matrix. Okay. So go back to the application we would like to share today about the Black-Scholes equation. We can the first step is that we transfer all of those differential operators of BS equation into the integral operators by multiple integration. We form that matrix A. Right. And then the second step is that we transform those integral operators into integration matrices through the nodal points allocation. And then this final step is that it's very similar, is the same as what we did in FIN. We construct that resultant matrix, that n plus p dimension square matrix, by introducing those boundary points. Right? In case you forget, it should be like this part. Because this part in black is our A, and then we have to edit other parts like those boundary conditions all together, this red one and blue one, to form this whole part is our resultant matrix. After we get this resultant matrix, we can get our approximation for our function u. So that is what we said, approximate option price evaluated at each nodal point by solving that resultant matrix. So this is the overall logic for the GFIM to solve the BS equation. Okay, this is our recent research, is that if we want to get a more accurate result and apply some boundary update procedures, the reason why we have to do this because when we solve some free boundary problems such as American option or exotic options, we have to update the boundary conditions step by step, right? So therefore, that is why we introduced this space-time decomposition, which means that for a given PDE, we can further break down the time interval into m disjoint union of subintervals, such that it is just a disjoint union, okay? And then give the PDE is then solved by GFIMST on each subinterval here. So I'm not sure whether you know that for the American option, usually we price from the backward, right? We price it from the maturity time. For example, here for m subintervals, we start from the interval t m minus 1, t m. Then after we get this approximation, then we use what we get here as a boundary condition of the formal interval. That is, we use the result we get for tm minus 1, tm as a boundary condition of interval tm minus 2, tm minus 1. So this is how these boundary updates work. Okay. So this is a brief introduction of what we recently find. So after all of these parts, let's take a look at some numerical experiments. Here's first one is we deal with the single asset European put option, and we benchmarked with the radial basis function. The first paper was written by my supervisor, Professor Horn, in 1999. So because it has very good results, so we benchmarked with RBF. And then we compare the GFIM and GFIM space-time, ST. The nodal points for the space dimension we use is 141, the same as RBF. And further, we increase it to 300. And then the dimension using by GFIM, we use 9. And for GFIM-ST, we use 5. We can see that even with less nodal points used, the GFIM-ST can give better results than the original GFIM. And further, for the GFIM-ST, the time decomposition, the time interval we choose is 0.02, very close to 0.024 by the RBF. You can see that the GFIM-ST can have very competitive result with root mean square error just 1.5 times 10 to the power of -4. Although you may see that the RBF is still hard to beat, that is because for the global RBF, it is very important to pick the optimal shape parameter. But here, for either the GFIM or GFIM-ST, we are free to select that optimal variable or optimal shape parameters. So that is why we suggest GFIM would be the better result. Okay, and also for this European put option, we tested the sensitivity of the delta t. That is, what kind of time step we choose, does it affect our term, our estimation? And we see that because our capital T, you see that the maturity time is just 0.5, which means that if we use delta T equals to 0.25, which means that we just update the boundary condition twice. That is really, really small. And we can get the error term as at 10 to minus 3 degree. And then if we further minimize our delta T, like from 0.1 to 0.005, then the result will be quite similar to each other. But further, we also tested that if we set the delta T too small, like 0.001 or even less, then the result will diverge. So therefore, for this kind of problem, we suggest that to pick the delta T within this range would be the best. And also, besides the sensitivity test of delta T, we also test the convergence of the nodal points selected on the space dimension. Because in our previous table, we set the dimension of space, the stock price, is 141. So we tested for 141, and half of it, like 71, double 282, and times 4, 564. We see that when the increase of the nodal points, then the error term would be minimized. The reason why this error term, although you see that the value is quite small, even the highest one is below 0.01, but the error term may increase around the strike price. The strike price E we set is 10. That is because for the option pricing, we have a turning point here, and that turning point is really hard to approximate it by this kind of polynomials. So that is why we get a little bit higher error terms around the strike price. Okay. But overall, we see from the table that overall the error term is already very small. So it doesn't matter, it is a little bit higher around the strike price. It is due to the limitation of this option pricing itself. Okay. And the second one is the American put option. The American option means that it is a free boundary question, so we do not have any exact solution here. So therefore, we use the binomial as a benchmark, and then we compare with the finite difference method, the radial basis function, and our GFIM space-time decomposition. So we see that when we have the highest nodal points and smallest delta T, we can get very good result compared to either the FDM or the RBF. And further, the last one is the 2SF exchange option. Exchange option is, the full name is exchange one stock with another, which means that you want to exchange your original underlying asset S2 into S1. So therefore, although the exchange option do not have any strike price, the strike price itself is 0, but we can regard it S1, S2, S1 as a call option and underlying S2 as a put option. You can just regard this exchange option as a combination of one call and one put. So therefore, in this result, because for the higher, for the high dimension, we cannot find even any benchmark, only by the Monte Carlo simulation, but that is, it is not accurate and costs too much time. So we only list what we find by the GFIM and GFIM-ST compared with the exact option price. And we can see that with higher nodal points and smaller delta T, we can get even better results. So also another limitation of the option pricing is that the boundary condition. The boundary condition itself for the option pricing, especially for higher dimension, it can be estimated, for example, by the Markov payoff function or the exact value of the PDE. So the result accuracy highly depends on the boundary condition you choose. So one should be very careful when choosing the boundary condition in the option pricing problem. Okay, so for the conclusion, the advantages of the GFIM, first, it is truly meshless, which means that it contains no mesh or grid are required. And then there are no restriction on uniform distribution of nodes, such as FIM. So which means that we can solve problems defined on the irregular domain. And also, it is very extendable to the higher dimension, which means that all these things you need to do is to choose the node points, the number of node points, and the degree of the piecewise polynomial you use to achieve a better result. And also, we can further improve the accuracy using the Chebyshev polynomial. This is also our potential future work. And we already tested it will perform even better than current state. And finally, but also very important is that GFIM is a very stable approximation. Although in some of the cases, it may not beat RBF as we shown before, but it is really stable. You do not have to choose any optimal shape parameters. So that is why we introduced this method to everyone. And yeah, here is the first work of the FIM, Finite Integration Method, published by Professor Wen and Hong and others. So if you are interested in how the formulation of the FIM, because in this presentation the time is quite limited, I cannot go into step by step, you are highly suggested to take a look at this paper. And also the first GFIM is published by my classmate, Sam, and also my supervisor, Professor Hong. And in this paper, you can find all of the proof for my previous illustration of the formulation, and also some very interesting examples to solving the high-dimensional PDEs. So these two papers are highly suggested. And here are some of the references related to our work so far. And then thanks for listening. Thank you.
Any questions from the audience?
Thank you very much for the nice talk. There are a couple of things that I would like to know because they are quite interesting. The first thing is about the inverse. You see, when you define the alpha from the the matrix.
This part?
Yeah, somewhere around the alpha. Not this one. The one that involves the inverse of x.
Here?
Yes, x here.
Yeah.
I would like to know how difficult to get this value.
Okay, you have a very good question, because this is what we encountered with in our numerical study. Because in some of the cases, the matrix may be too singular to get the inverse. So we are working on one method is to inverse this matrix line by line, which means that we do not inverse it at the same time. We invert it into, separated into several pieces to do this inversion. This is really the problem we may encounter this, but I think we already have some idea on how to solve that. Okay. Still, it is a very good question. This is what we encountered already. Yeah.
I think one more question about the American options. Somehow, if you look at the boundary for the exercise, is actually not known, right?
Yeah.
And how did you handle this thing? Do you have to think of this like solving using Newton method or something like that? Because it's not known, right? It's not known, even though you. How did you handle?
I know what you mean. So you mean that because for the American option it is free boundary, right? We do not have any exact solution. So that is why we try to use this space-time decomposition. We use the approximate result from the last interval, and then use this result as the boundary condition of the previous one, and then go from the very last to the very beginning, step by step.
It's like
so
you're moving backward, right?
Yeah, step by step. So that is why if we choose suitable delta t time interval, then the result will be better. But if the delta t is too large or even too small, no work.
Oh, okay. Thank you.
Do we have more questions?
It's really fun too because it is also the first time I represent this talk. So in case something wrong, just let me know.
Okay, if no question from the audience, then we would like to thank Ms. Zhang again.